Shape is very important because it determines properties. We can determine the shape at a central atom by using valence shell electron pair repulsion theory. The number of bonds and lone pairs determines the shape at the central atom. For example, the carbon in methane has 4 electron pairs, which means it has a tetrahedral electron pair geometry. All the electron pairs are bonding pairs, so carbon has a tetrahedral molecular geometry, which matches the electron pair geometry. Ethanol has 3 central atoms, so stop the video and determine the shape at each central atom using VSEPR theory. So here are the answers. Carbon 1, which is this carbon, has a tetrahedral geometry because there's 4 bonds and 0 lone pairs around that carbon. Carbon 2 also has a tetrahedral geometry, 4 bonds, 0 lone pairs. Oxygen is bent because there's 2 bonds and 2 lone pairs. So remember those lone pairs, which fits the octet rule for oxygen. Let's practice some more. So stop the video and determine the shape at each central atom for propyne. So here are the answers. Carbon 1 is this carbon, here's carbon 2, and there's carbon 3. Carbon 1 is linear because that carbon has 2 bonds to it, the carbon-hydrogen bond and the carbon-carbon triple bond. Now remember, treat a carbon-carbon triple bond the same as a single bond. Carbon 2 is also linear. Again, treat the carbon-carbon triple bond the same as a carbon-carbon single bond. And carbon 3 is tetrahedral. So here's some more practice. Stop the video and determine the shape at each central atom. Carbon 1 is this carbon. Carbon 2 is either this carbon or that carbon, and also for nitrogen. So here are the answers. Based on structure, we can determine shape using VSEPR theory. From shape, we can determine whether a molecule is polar or nonpolar. Polarity tells us properties such as solubility. So this molecule has polar bonds, so stop the video and answer this question. Is this molecule polar? And the answer is yes. This carbon is tetrahedral. The carbon-bromine bond is a polar bond. The 2 carbon-hydrogen bonds are slightly polar. The carbon-carbon bond is nonpolar. The relative polarities of those bonds and the tetrahedral shape at that carbon makes this molecule polar. So again, look at structure, shape, and then determine polarity. So stop the video and determine whether these compounds are polar or nonpolar. So here are the answers. So remember, water is polar because of its bent shape at the oxygen. The oxygen ethanol also has a bent shape. So if we replace the H by this group here, it still makes that oxygen bent, and that makes ethanol polar. For this compound, which is aniline, note that the nitrogen has a trigonal pyramid shape. And for this molecule, propyne, note that the carbons here have a linear shape. Organic compounds are classified by functional groups, so stop the video and answer these questions. Functional groups that contain oxygen are blank. Hydrocarbons, whether they're saturated or unsaturated, are blank. And then fatty acids, an example is this structure here, are insoluble in water. Why? So here are the answers. The main part of a fatty acid molecule is nonpolar. That's why fatty acids are insoluble in water. Structure determines shape, which determines polarity, and polarity helps determine the intermolecular forces between molecules in the state of matter. These intermolecular forces help us determine properties such as boiling point and melting point. So London force exists in all substances, whether they're polar or nonpolar. Dipole-dipole force exists between polar substances only. Hydrogen bonds are a special case of a dipole-dipole force. There will be a hydrogen between 2 very electronegative atoms on 2 different molecules. The electronegative atoms are fluorine, chlorine, oxygen, and nitrogen. So let's practice. Stop the video, determine the intermolecular forces in each compound. So here are the answers. Ethanol, which is polar, has London forces, dipole-dipole forces, and hydrogen bonds. The hydrogen bonds are shown between 2 different ethanol molecules with the blue dotted line. Propyne is nonpolar, so there's only London forces only. Aniline is polar. We'll actually see London forces, dipole forces, and a little bit of hydrogen bond between aniline molecules. So that dotted line shows a hydrogen bond between the nitrogen and hydrogen on two different aniline molecules. Intermolecular force between molecules in the state of matter helps us determine boiling point and melting point. So stop the video and answer these questions. So here are the answers. An important application of structure, shape, and intermolecular forces is how a drug interacts with a drug receptor. This molecule is the opioid morphine, codeine, or heroin, depending on the R group. The opioid binds to the opioid receptor as a result of these structural features. The benzene ring is trigonal planar each carbon. That's what makes it flat. That binds to the flat area of the receptor. The ethylene bridge is accommodated in this trough in the receptor. Under physiological conditions, the nitrogen accepts a proton, which gives it a plus charge, and that forms an ionic bond to the anionic site of the receptor.